Hello again, everyone. Perhaps first of all, introduce myself. My name is Ronan Piedevache. I am a student master at the University of Rennes in Brittany in a Master of Theoretical and Applied Physics that offers a course fully dedicated to photonics. And the idea of this short talk is precisely to present to you the work that I was able to carry out these last months during my summer internship that I could complete in the laboratories of Photonics Bretagne in Lannion under the supervision of Stéphane Perrin, who I guess is in the audience, who is the project manager of its biophotonics team. And this internship dealt with beam shaping for hyperspectral microscopy using single pixel imaging techniques. And to give a bit of context, I arrived in a structure, in an environment where this specific combination of hyperspectral imaging and single pixel imaging is something that, as you perfectly know now, is something that has already been experienced by the teams of Photonics Open Projects and Photonics Bretagne, who built up in the last few years this hyperspectral macroscopic imager, as Leo presented, which allows one with a very compact and easy to use device to execute every configurable steps necessary for single pixel imaging, starting from the spatial modulation by projection of patterns through the acquisitions of Fourier hypercubes and to the digital reconstructions of hyperspectral images. And to this day, this device is mostly used for indoor measurements of plant species, such as this one, where you can see a scene where is placed a plant of Chevignon wheat. And in the center is precisely the physical object that we acquire, the Fourier spectrum, Fourier hypercube to be precise, of our scene, on which we will rely on to digitally reconstruct the hyperspectral image of our scene. And you can already guess that even with an ever better resolution, here the resolution is 71 × 71, even with an ever better resolution, you can quickly find yourself faced with a certain limitation regarding the level of detail that you can have. Typically, it is difficult to have access to details below the scale of the millimeter. So it's with this observation that my internship project quite naturally was, with this objective to overcome this millimeter limit and to transpose the operating principles of the ONE-PIX system to a more microscopic scale in order to gain in spatial resolution. So in one word, the idea is to develop and design a prototype with the same pieces of equipment used for the ONE-PIX of Fourier transform, single pixel, and hyperspectral microscope. And to build such a prototype with this kind of equipment, commercial equipment, well, we kind of started from zero because it has no real precedent in the scientific community. But we did have certain technical specifications that we used based on literature and that guide us through this project, both on the hardware and the software level. On the hardware level, our prototype has to be centered around two main blocks. On the one hand, an illumination path in green, which aims at form the Fourier patterns at the heart of single pixel imaging techniques on a microscopic sample. And in this case, we talk about structured illumination microscopy. And on the other hand, a detection path in red, which aims at converge the light response of our sample towards a point detector connected to a spectrometer. And on the software level, it is per se much simpler because we already had at our disposal powerful and efficient digital tools, the algorithms used in the ONE-PIX system that we had to adapt, of course, to the microscopic scale. So the first big part of this internship was essentially focused on the development of this system, the illumination path that is here. And unlike classical microscopy, which uses homogeneous white light illumination, here, as I said before, the objective is to project Fourier patterns with a commercial video projected and to form them on a sample plane run here and through a microscope objective, in this case, with a 20 magnification. So, of course, this imposes a huge work, a significant work on the beam shaping of our illumination beam. That's why we introduced a relay lens system, which by combination of focal lengths allows us to reduce by a factor 3 the diameter of our beam and to better inject it through this objective. We also placed two optical density filters in order to better control the luminous flux that we project into the system related to the intensity that will be focused on the sample plane here. The idea is not to damage or burn our samples. And also a first beam splitter in anticipation of the detection system in this direction, because actually we work in a reflective configuration. That means that our illumination system and our detection system will share at some point the same optical axis. And in single pixel imaging, you must keep in mind that the level of detail that you will get in the end on your reconstructed images is fully determined by the smallest spatial period you are able to project on this sample plane here. That's why this system is of capital importance, because it actually has to absolutely miniaturize the projection process of single pixel imaging while preserving the periodicity of the patterns and limiting as much as possible optical aberrations or deformations. And with this precise configuration, that's what we managed to do, as we can see here on this set of images acquired in the sample plane with this small monochrome camera. And you can see that we managed to obtain miniaturized Fourier patterns with spots of about 1.5 millimeters of diameter. And that we also managed to vary both their spatial period, lambda, and their orientation angle, alpha, in order to perform Fourier transform single pixel imaging to scan the Fourier space. So that's first good point of satisfaction to be able to form and to visualize these miniaturized patterns. But now that we can visualize them, the idea is to characterize them and to estimate the resolving power of our system. And one possibility to do that is to go through what is called the modulation transfer function of our system, the MTF, that allows us to estimate how our system is able to restore contrast and even to highlight the potential presence of optical aberrations. And how can we plot this function? Well, if you take a random pattern associated with a certain spatial frequency, you can plot an intensity profile in a perpendicular direction compared to the directions of the fringes. And based on this intensity profile, you can compute the mean value of your contrast of your pattern. You then repeat the operation for several spatial frequencies in order to obtain this kind of evolution curves, very characteristical of the behavior of an optical system, with first a plateau and then a drop of contrast. And with these evolution curves, you are able to estimate the cutoff frequency of your optical system, which is related to the smallest distance that it is capable of resolving. And in our case, with a contrast threshold of 20%, we found out that our system, the cutoff frequency of our system, was about 40 millimeters minus 1, which corresponds to a distance of 25 micrometers. In other words, with this version for our illumination path, we are able to resolve details of about 25 micrometers, which is an excellent starting point, considering that we are only using a microscope objective with a 20 magnification. And the question that we can ask ourselves now is, with this level of performance, is it possible to acquire hyperspectral images of microscopic scenes? Of course, in theory, we are tempted to say yes, but when we move into practice, it is always a bit more delicate. And that's what the second part of my internship was about, really the acquisition aspect of the project. And before throwing ourselves into these acquisitions, we first had to decide what we wanted to image, because actually there are no such things as commercially available microscopic scenes that we can use as spectral references. So we kind of had to design our own homemade microscopic scenes. The one that you can see here is the one that we used the most. It's just a sheet of paper with printed colors on it, green, yellow, blue, and red, and onto which we also taped an optical fiber with a copper coating. And in order to have a fairly identifiable scene, we aimed with our illumination beam at this little area, which corresponds to the center of the sheet of paper where all the colors meet. And to clearly visualize the details of this area, which is kind of difficult with the naked eye or even with pictures like this, we decided to introduce in our detection system a small RGB camera, providing us this kind of microscopic images, where we clearly recognize the junction of the colors and also the optical fiber crossing diagonally. And to give you an idea, the diameter of this optical fiber is about 125 micrometers. And the advantage of having this kind of microscopic images is that we can use them as references to compare them to the reconstructed images that we will get with monopixel acquisitions. And speaking of which, the first acquisitions that we performed them with this, I would say, basic configuration for our detection system with just the point detector placed at the end of our detection arm and the connection with the spectrometer. And I have to say that the first results that we get were quite bad, actually, because the reconstructed images were mostly dominated by a black frame, a very disturbing black frame with a small luminous spot, as if the point detector didn't collect enough light from the sample. So we first had to identify the causes of these unsatisfying results. And we realized that it could be explained by two main phenomena. First of all, we realized that our illumination path caused an excessive cropping effect of our patterns that tremendously influenced the framing of our reconstructed images. As a matter of fact, we projected way too big rectangular patterns through optical components with a spherical shape. And so only a small part of the surface of our pattern actually reached the sample, and the rest was completely blocked by the several components of our setup, especially the lens entry, the entry lens of our objective. So to overcome this, it was necessary to further miniaturize our projected patterns so that they pass entirely through this lens entry corresponding to the red circle that you can see here. And the first solution to do that is to materially modify our assembly to limit as much as possible the overflowing light beam you can see here. To be precise, we changed the focal length of our lens L2, which is the second lens of our relay lens system, in order to better inject the illumination beam through the objective. And you can see that it allowed us to slightly improve things with an increased miniaturization, even if there are still portions of the patterns that are cropped, that are blocked by our setup. So our second solution is to play not on the hardware level, but on the software level by directly touching to the source code of our acquisition system in order to digitally resize our projected window, moving from a big rectangular window to a small square window that fits perfectly or quasi perfectly with the lens entry, the entry lens of our objective, and that reach entirely our sample, as you can see here. And the results of this modification, they are immediate, because we went from this kind of images, as I said before, dominated by a black frame with a small luminous spot, to images where the spot is much larger and where we even start to distinguish some details of our microscopic scenes. But you can also see that a black frame remains. And so the second problem didn't concern our illumination path, but instead our detection path, because actually we used a light collection system with an optical fiber that generated a lot of vignetting effects, that is to say, the darkening of the periphery of our images. And so once again, to correct this, we had to bring modifications to our detection path by introducing before our collection fiber, which is our point detector, a converging lens in order to focus the light coming from our sample and to adapt it to the field of view, the FOV, of our point detector. And we even noticed that the position of this point detector, this collection fiber, played relatively to the lens L4, played a determining role on the intensity of the vignetting effect. As you can see here on the set of acquisition results for different distance d between the collection fiber and the lens L4. And you can see that with this distance, we can change the intensity of the vignetting effect, moving from a very shady transition between this luminous spot and the black flare to a very clear delineation between this spot here and the remaining black frame caused by the cropping effect, as I mentioned earlier. So that's great because we wisely modified certain characteristics of our setup to both reduce cropping effects and vignetting effects in order to, for the first time, to acquire hyperspectral images of microscopic scenes, which constitute truly first experimental results. But of course, the ultimate goal of this project is not to acquire hyperspectral images of sheets of paper, but rather have interest in biological samples. That's what we attempted to do at the very end of the project by trying to image the cellular tissue of an onion skin. And I know you're probably saying to yourself that there are way more interesting things to image than an onion skin, and you're right. But the advantage of the onion cells is that first, they are quite big, of about 100 micrometers long in average, which is very in line with the first estimations of the resolving power of our microscope. And second, that its cellular tissue is quite identifiable with this straight and periodic layout that is very easy to identify. And you can once more see that we managed to extract spatial information from the scene, both on the Fourier spectrum with where the vertical layout of the onion skin clearly stands out, and also on the reconstructed image, where we can begin to distinguish certain cell membranes. And by the way, you can once again testify of the clear delineation between the black frame and the luminous spot, which means very few vignetting effects. So perhaps the results are less visual than the previous scene, but as a first application to the observation of biological tissue, those are very encouraging experimental results that constitutes concrete proof of what our prototype can and will do. And to quickly conclude on this project, well, we managed to, within this 4-month project, to set up a functional prototype of hyperspectral microscope using single pixel imaging techniques, and with us provided low-cost technical solutions, material solution, to perform structured illumination microscopy using single pixel imaging with an illumination system that allowed us to miniaturize the process of pattern projection. And we also managed to obtain first encouraging, convincing, and promising experimental results by acquiring first hyperspectral images of microscopic scenes, especially biologic scenes. So that truly constitutes a first proof of concept that demonstrates the feasibility of the techniques that we try to associate with a commercial pieces of equipment at the microscopic scale. And thanks to this work, we can hope to open a whole new area of research within the departments of Photonics Bretagne and Photonics Open projects. And because of the compatibility of our system, our prototype with the ONE-PIX, of course, it will benefit from every improvement of the software part, which are still work in progress, as you testify today. But not only on the software level, also on the hardware level, because the idea is to move from a demonstration version mounted on an optical marble to a fully integrated version, more robust and transportable. And precisely, the ONE-PIX system is ideal for this purpose, because we can easily imagine an extension that we can fix to the ONE-PIX kit in order to get a really great device that combine both hyperspectral imager on macroscopic level and on the microscopic level. So those are truly exciting and promising perspectives for the month and the years to come. And before I finish, there are a few persons I would like to thank. First of all, the teams of Photonics Bretagne who welcomed me this summer, and especially my supervisor, Stéphane Perrin, who brought his perspectives and his precious pieces of advice for this project. Thank you also to the team of Photonics Open Project, Gaspard, Antoine, and Mathieu, for first showing interest in this project, and second, for giving me this opportunity to talk to you today. Not every master student have the chance to present their project in front of such an audience. So thank you guys for that. And of course, thank you to every one of you who connected today. And if you have any question, I would be pleased to answer them.